start with a few caveats. The first is, you'll notice Martin Scheringer's name has a star next to it because this was originally meant to be his presentation. When I was asked to provide a title for this, this was way before I knew what I was actually going to present, so I was very ambitious. I was going to talk about these pragmatic approaches to environmental modeling in the context of regulatory environment. But what I'm actually going to present to you are two, I think, really nice examples of what has come out of our group for just the power that models have at very different scales. And then in the end, hopefully I'll have enough time to talk a little bit about work that's been going on recently with the IBCCF, the International Panel on Climate Pollution, and how we're really looking to provide a useful interface between scientists and regulators. So to begin, I work in a group where all we do is modeling pretty much. There's nobody collecting data, and so we often get questions. What exactly is the utility of modeling for people? Because for some people, modeling is really just correlation with data. But models have a lot of power beyond that. So there's a very, very nice little article written by Joshua Epstein in the Social Science Journal in 2008 called Why Model? And people who are interested in modeling, I think everyone should read this. It's only a 2-page article. But a very nice quote to come out of that is, all models are wrong, but some are useful. So we know that models are simplification of real life. And what we want to find are models that are useful to us in some way that can give us insight into the data that we are able to collect. So aside from just providing correlations with existing data, models can be used to do things like explain phenomena, guide data collection, discover new questions, bound outcomes to plausible ranges, illuminate uncertainties. And one thing I always find really interesting about using models is that often they're able to reveal something that looks simple to be complex, or something that looks complex to actually be quite simple. And of course, models can be used to help discipline policy dialogue. We're trying to understand what's going on in the midst of what might be confusing or conflicting data. An environmental big model in general can really be used as an integrated platform to understand what's going on in the environment. And there are 4 main components to this. So here I'm just using the climate model. It's a model that's developed in our group as an example. The model is basically just a description of the environment, and it's a framework that we use to investigate phenomena. And important are the inputs and the outputs, of course. So the inputs to the model will be your chemical properties like partition coefficients, degradation half-lives, degradation speeds, and things that are really important like emission inventories, which people who are working in environmental chemistry are really interested in, spatial and temporal distribution of chemicals. And then putting these things into the model framework, you get some sort of result out of that. Concentrations, mass fluxes, metrics like persistence. And the crucial bit that sometimes gets left by the wayside is this interaction between the model results and the field data that are available. So field data are not just something that you say, the model matches, it doesn't match, so the model failed, it didn't fail. It should be an integrated and two-way process here. So looking at field data, measurements of concentrations and mass fluxes can tell us what's missing both in the description of the environment in our model, but also in the field data itself. And then you can even link it all the way back to things like your emission inventory. Maybe there's something you're missing in terms of the source. And all these things can be investigated by looking at all the components together. And multimedia box models, are just one kind of environmental model, but they're really convenient as an analytical framework because they are almost endlessly flexible. So they can be very, very simple. You can just have a really simple model where you've got air, soil, water, and you're looking at the exchange processes between them. Depending on the actual question you're trying to investigate, you might want to add things like precipitation and pesticide models. Ice and snow, if you're looking at more polar latitudes. Exchange between aerosol particles and the atmosphere. Export to the deep sea, if you're looking at reservoirs for chemicals. So I'm going to try and hopefully show 2 examples of an effective use of models that have been done in our group. So the first one is kind of an old case. And when anyone talks about PCBs, well, PCBs have been about for a long time. They're already in the Stockholm Convention. So the main questions here are, is regulation effective? So PCBs are already listed. Do we know what we need to know about them? And then maybe a little bit about how interaction and collaboration can work in this case. We're going to be talking about emissions levels and trends in a very localized application. The second example is looking at endosulfan, which has come up time and again during this workshop, so I think it's on everybody's mind right now. And here is some work that was done between Martin Shanaker and one of our master's students, Lynn Specker, looking at endosulfan distribution globally in the atmosphere and in the oceans. So I think everyone's pretty well aware it's a contentious candidate for POPs regulation right now. Contentious mostly because of one party. What can you do? Okay, but what can be said about levels of trends in the environment using data we now have? And what do the models tell us about the state of our knowledge? And then hopefully I'll have enough time to talk a little bit about the IBCCF. So we'll start off with the PCB example. So global PCB emissions. Breivik did a very comprehensive look at global PCBs. We know that there are several diffuse sources out there: electrical equipment, paints and joint sealants, lubricants, hydraulic fluids, many more. We know that the emission of PCBs peaked around 1970 before they were banned in much of the world at about 1,000 tons per year. And this is from just a measure of how much PCBs have declined in percentage since that peak in 1970. You can see it's a fairly drastic decline. So what does this mean in terms of the problem being solved? We know that PCBs were part of the first original Dirty Dozen in the Stockholm Convention, so they're supposedly been taken well in hand. Banned in many countries since the 1970s, but I think most of us would agree that the problem is not solved. And at this point, it's moved from a problem of emissions to a problem of containment, treatment, many dilute sources of these leaking transformers. And so, one of the projects I've been working on with Glenn Gossick, who is now a postdoc, at least for the next little while, is measurements of PCBs in Zurich. And I've now lived in Zurich for 2.5 years. And it's not a city I think of as being one of these problem hotspots for contaminants. It looks like a pretty clean place. And it's not a very industrial city either. So they wanted to look at two sites. Zurich City itself. This is a site near an environmental measurement station. It's about 446 meters above sea level. And this is Uliberg. It's Zurich's only mountain. It's not very big, 157 meters, but people like to go up there and see the view over the lake. So there's about a 400-meter difference here. And they wanted to investigate the city of Zurich as a possible source of PCBs, because there has been recent work in a lot of different places. For example, Chicago identified as a source of PCBs, or everyone thought they'd be the Great Lakes, it's the other way around. So there's evidence out there for cities as being sources. And so the sampling campaign was essentially looking at day and night time levels of PCBs in the atmosphere over a period of 3 days. So here's a little picture of the site. Here's a view of Zurich and the lake. That's oil, going into most of this work. And they used a set of high volume air samplers that were deployed. These use puff samplers, and they run for a 4-hour period, and they're changed every 4 hours continuously over 3 days. So definitely work that sends some students off to do it and wait for the results to come back. So the model structure used here is based on the better model framework that Matt McLeod developed, who has just left our group now at Stockholm. And it's a single region implementation. So here we're really looking at a small region where we're modeling the air, and we divide this into upper air and lower air, vegetation, soil, and water. And we're looking at things like airflow. So up to 7 environmental compartments. It's a non-steady state mass balance model. So we're really looking to follow the time trends dynamically. And the important drivers here are temperature, the mixing height of the atmosphere, and wind speed. So what features about this are really going to be important in terms of determining what's happening in the two sites? Well, the dial cycles and mixing heights, when you're looking at stable atmospheric conditions, are really important to the dynamics of PCB between day and night. And this is because what happens at night is you get this nocturnal boundary layer that happens. During the day, the terrestrial surface warms up and you get convective mixing up to heights of above 1 kilometer. And so the atmosphere is fairly well mixed. At night, however, the soil surface cools more rapidly, and so you get this inversion where you have stable boundary layer and no mixing occurs. And there have been measurements done in the Zurich area that show that this nocturnal boundary layer is on the order of 100 meters high. And this means, if you look back at our sites, that the city of Zurich is going to be impacted by this boundary layer, but Uliberg will not. It's above that. So it's not in this capped area. So the important parameters for the model then are this atmospheric mixing height, temperature, hydroxyl radical concentration, and speed. And then you can see, if you're thinking about the two different models, if you look at the Zurich City one, you expect the difference between the daytime and the nighttime to be something like this. During the day, you've got lower air and upper air that are well mixed. You've got high temperatures, OH radicals present, and then in the nighttime, this nocturnal boundary layer forms. You no longer have the mixing here going on. And now if you look at the results, we're starting at Lüttiberg. We know that there we don't have the effects of the nocturnal boundary layer, and we suspect that the only source to Lüttiberg is PCB source and background air inflow. So that's used as what we're trying to model here with the data. Concentration maximum that are found are during the day. So this means that there are more PCBs at Lüttiberg during the temperature highs in the middle of the day than there are at night. If you look at the results for Zurich, on the other hand, we suspect the PCB source in the city itself, and we find the opposite is true. Concentration is maximum at night, so we have the opposite cycle there. So the hypothesis is that at Lüttiberg, what happens is PCBs are getting mixed into the atmosphere in the city during the day when this boundary layer is not in effect, and then is coming in with the background concentration, causing a maximum at Lüttiberg. Whereas at night, when that volatilization is capped from the city, then there's less PCBs that are coming into Lüttiberg. In Zurich City, on the other hand, you have a maximum during the night when the cap is over the city, and you're having an accumulation of PCBs, and then when the temperature heats up and this inversion layer disappears, you have mixing into the atmosphere. So there have also been some studies that have shown that perhaps OH radical reactions happening during the day could be responsible for this depletion, but they actually found, trying to fit this data, that the only thing that could really explain these drastic high lows was mixing into the atmosphere. So it's a dilution effect when the boundary layer disappears. So the conclusion from this modeling exercise is that Zurich is a strong source of PCBs. So they estimated that in the urban areas you get about 600 kilograms per year of PCBs to the atmosphere. And that's actually pretty large for a place where you don't have any industrial activity. Zurich has a population of about 375,000, and most of the industry there, most of the commentators in the service sector. And so this 600 kilograms per year are coming largely out of buildings. So this is the joint sealant issue. This is an issue that's going to be around for a long time once we demolish all the buildings and somehow hide that PCB somewhere. It's also about 3 times higher than the per capita estimate that Breivik had estimated in that paper we did the global emissions based on bottom-up calculations. There are a lot of reasons for this. This could be due to higher temperatures when we're measuring, so increased volatilization because all these samples were taken during August. It could also be particular to where we're looking. But the really nice thing about the results of this study is that if you look here, it did a pretty good job of capturing data that could, on its own, look fairly messy. And really, the only thing you needed in order to be able to capture the features of the data are to understand the dial cycle, the emission from the city, and these day-night inversion layers. So now I'm going to talk about a very different example of looking at endosulfan in the atmosphere and the oceans. So whereas for the PCB model, we're looking at a very local site, now I want to take it to a global perspective. The objectives of this study were to evaluate the persistence of long-range transport of endosulfan in the global environment. If you remember, we talked about the requirements for something to be listed in the Stockholm Convention, which would also include bioaccumulative potential. But the persistence of long-range transport are kind of the bread and butter metrics that our group likes to investigate. So focus on this. And they wanted to do a thorough and systematic job, and so for persistence, they were looking at time trends for measurements and laboratory testing field campaigns. There's actually a bit of data available for endosulfan because there have been a lot of air monitoring campaigns in place. Field data showing spatial distribution of endosulfan, and they also wanted to include both alpha and beta and the degradation product of sulfate. And here, rather than this small box model, we're looking at a global model, ClimaChem. And this model has been validated before in studies on PCBs and DMTs already. And it's an interesting model because it's the geometry is just these latitudinal bands. So we assume that everything is homogeneous along the longitudes, and so what you have is just this axis from sort of north to south poles. And the purpose of the model is really for mechanistic analysis of long-range transport. So it's got these latitudinal bands that contain soil, water, air, vegetation, ice, and snow. And the vegetation and ice and snow are built in based on remote sensing data. So there's a lot of parameters that go into this model. And each little subsection here looks like more or less the structure of the previous model we used for Zurich. So this just shows you how we take remote sensing data like this that looks at types of vegetation along the latitudinal bands and translate that into the model. And similarly for ice and snow. I wasn't involved in the work in developing Medicine, but I know that this was a big challenge to build ice and snow modeling into here because of these features that snows change density and water content, the dynamics of snow melt over time to look into. Air-snow phase partitioning is not necessarily well understood, but it's actually going to be fairly important. And then, of course, you have to look at the important inputs in terms of the chemicals of the model. So we needed things like partition coefficients and degradation half-lives for all of them. These are log AW, log AW, which are chemicals. And then also we need partition coefficients, which we just see, but the degradation half-lives are really important because we're looking at persistence and we're looking at long-range transport potential. So we need to know how long they're going to be in the environment. Luckily, there were experimental data available for most of these. The only thing that had to be estimated was the degradation rate in air. So for that, we used AOP that comes out of Episweep. I don't know if you guys can handle it. For water, there were experimental data for hydrolysis in seawater, and for soil, they were based on an assessment by the UFRJ. But because all these properties, in particular degradation rates, are really important, we also performed an uncertainty analysis to see how uncertainty in these values would propagate to model results. And then, of course, they also needed some sort of degradation scheme. So they used a simplified degradation scheme where the only metabolite they were interested in is indole sulfate. And then here are the two isomers alpha beta sulfin and indole that were used, released at a ratio of 7:3, which is normal. And they assumed that when it was used, 90% went to vegetation-covered soil and 10% was emitted to air. So then the next really big part of this study was to figure out what the emission data would be. And the first step in that is to use use data. So they had usage data, and they assumed some emission out of that usage data. So the total historical usage was about 300,000 tons, so this is from essentially the second half of the last century. The problem, of course, is you had a global model that you want to solve on a time-resolved and regional basis. So you need to somehow figure out what the contributions for the different latitudinal zones are. And luckily, they were able to get some data from their crop sciences and the FAO. And so they calculated contribution from different latitudinal zones from the north and the south based on crops. So they looked at crops where indole was traditionally used. And there are seven major ones: cocoa, coffee, cotton, fruits, soy, tea, and vegetables. And using that, they basically divided up the total budget of indole. So here we have the contribution from the different latitudinal zones, and this is the input in tons per year of the emission. These are the zones running from north to south. And I just thought this was sort of interesting. They've got here based on 1995, 2000, 2004. I just thought it was interesting to see the switch where 1995, the north dominates a little bit, and beginning 2000, the south kind of picks up. So here are the results from the concentration in the air of indole. So the field data are in these pink circles, and the model in these lines. And in general, for air, we got fairly good agreement, especially in the Arctic regions. And then it gets a little bit fuzzy as you go south. So you can see that in general, the latitudinal trends are okay, and the ratio of alpha, beta to sulfate are also okay. Concentrations in ocean water were more problematic. So we've got more limited field data, very little field data available for indole and sulfate, which is 1 point. And all three substances, the model is off by about a factor of 10. So the model is underestimating the amount that actually present in the oceans. And possible reasons for this are that the activation energy of hydrolysis is too low, or the half-life in water is too low. And this is kind of where they're leaning now to thinking that the half-life in seawater should be higher, particularly for regions. And then one of the most interesting things that came out of it is if you look at the field data for time trends in the Arctic, it's got a very odd distribution. So maybe it's a little difficult to see in these data, but you essentially have a bimodal distribution with peaks in the spring and the fall. This is for alpha endosylvan. If you look in the temperate regions, it just looks like a peak in the summer, which is more or less what you expect. High temperatures and higher use, as all the temperate zones are emitting endosylvan only in the summertime. So they wanted to figure out how can you possibly get this into the model. And this goes back to climate change capability to include snow and ice. Because the formation, so if you looked at alpha and beta and endosulfan sulfate, you would see that alpha and beta both follow this trend, whereas endosulfan sulfate has one peak in the middle. And what happens in the Arctic is alpha and beta come in through atmospheric deposition, whereas the sulfate is formed on the soil once degradation of the other two occur. So what happens is during this time, deposition is occurring to mostly snow and ice, because during the spring and the fall, much of the land surface is covered in snow and ice. And deposition to snow is much slower than deposition to soil, because the sorptive capacity of snow is smaller. And they looked at the mass transfer coefficients between air and snow versus air and soil, and they have a difference of about 5 to 10 meters per hour for snow versus 25 for soil. So what happens is, when there's snow available, deposition is slow, and then in summer, when the soil becomes uncovered, the deposition rate increases dramatically. So you get this well right here. And then the other thing they were looking at is what fraction of endosylvan from the Arctic comes from different places, different zones. And this also has to do with not only use, but with distribution of soil versus water, for example, is available. So they just broke it up in terms of north temperate, north subtropic, north tropic, and looked at the share of emissions, the transport distance to the Arctic, and then the share of contribution. So you can see that emissions were highest in the subtropic region, but contribution was highest from the temperate region, and you can see the different distances that are involved there. So if you look at the joint persistence, and if you're not familiar with joint persistence, it's just looking at the sum persistence of alpha, beta, and the sulfate. Persistence including all of these, as well as it is formed continuously in the environment, is strongly influenced by half-lives in the largest reservoirs. And here, the largest reservoir is soil, because that's where it tends to end up. Where there isn't a lot of soil, ocean water becomes more important. The joint half-life of the family of all three substances in the global environment is like 430 days. So the global environmental phase of alpha and beta sulfan and the sulfate can be reproduced using this model fairly well. We have some problems in the ocean water. The model enabled us to do a consistency check for emissions, chemical property data, and field data. So in air, there was fairly good agreement, but there is a discrepancy for levels in seawater, and this is probably because there should be higher half-lives on the order of 4 to 5 years at least in polar environments. Shorter half-lives are unlikely. And all regions of the globe contribute to presence in the polar region, so everyone is making some contribution, but there are different shares. And it's not just based on emissions, but it's based on emissions plus the characteristics of the environment and the distance traveled. So to go back to where I started with this model thing, and thinking about both of these cases, it's important to realize that all models are idealizations, and the issue is whether the model offers you a fertile idealization of what you're trying to do. Model results depend largely on the questions we ask, so we need to keep that in mind. Whereas some models can be used in a more exploratory fashion to point us to what the important questions should be. Where are the gaps? This is another quote from that article by Josh Epstein. Modeling enforces militant ignorance. I kind of like that. A commitment to I don't know. You have to keep telling yourself, you might have a hypothesis, you kind of know where it's going, but you have to be open to whatever result comes out and investigate what that means. So hypotheses are okay as long as they don't evolve into expectations. And models can really be focal points for teams involved in many different disciplines. I think this is especially true for environmental science. I'm sure most of you agree that even looking at this group and the very different backgrounds we all have. And often we need this outside expertise to see things that we don't see. based on our own experience. And finally, models don't obviate the need for judgment, but they can discipline the dialogue about options and make unavoidable judgments more considered. And this really kind of gets us more to the policy. So that brings me to talking about the IBCC, which is really envisioned as an interface institution between science and policy. So how can we take the stuff we do as scientists and make sure that it's used in a way that we appreciate? I think a lot of scientists kind of gripe about, we work really hard to get good results, and then they just go and do whatever they want. So maybe we should try and do something about that. So environmental chemistry, toxicology, all these different disciplines have a lot to offer to policy. But the implementation of scientific results needs an effective transfer of knowledge. And I think a lot of the problems we find as scientists is we don't speak the same language as regulators all the time, and that can get in the way. The transfer of knowledge isn't demanding just because it requires this mutual understanding. So what are the obstacles to this transfer of knowledge? Information is often not available because the needs of users don't overlap with the interests of the ethics of scientists. Sometimes scientists just want to do the stuff they're interested in. Maybe it's not necessarily what users are interested in. Sometimes scientists aren't aware that there are users and they need stuff. So there's also a format mismatch. Scientists aren't aware that users may not search for journal articles. They say, we don't know anything about this, and the scientist says, well, just publish that as a journal of obscure something or other. How can you not know? And scientists don't have the capacity to present results in a different format. So we're already pretty busy trying to go to workshops and conferences and telling people about what we do. And it isn't really our job to get this information to them necessarily. Maybe we don't have the capacity to do that. And importantly, this additional effort isn't really appreciated by academic environments. People don't say, that guy is a great scientist because he goes and talks to people at UVA. They say, that guy's a great scientist because he has newspapers in Nature. So there isn't really a appreciation sometimes. So how do we transfer this knowledge? The mismatch of objectives is really not a failure. We are in two different worlds, but it's a consequence of the different inherent structure of academic science and politics administration. So here are some possible scenarios. Here's academia, here's government institution, here's a scientist who's busy working on his stuff and publishing in journals. And the scientific officer is looking for these results, but he doesn't know where to go. Or you can have a case where they're actually both trying to find each other, they're just not really sure how. So really what the IBCCF would like to be is this interface institution that provides that link so he doesn't have to work too hard, he doesn't have to work too hard, and figure it out. There are already a lot of existing interface institutions. So the IBCCF is not this brand new idea. So there's some really well-known ones like AMAP, the Arctic Marine Assessment Program, EMAP, part of the Long-Range Transatlantic Air Pollution Program, the International Program on Chemical Safety, that's part of EMAP and the WHO, and others. But the thing to keep in mind also is, and we talked a little bit about these 3 days, is that there are tens of thousands of chemicals out there. They have many possible impacts, and there are many, many stakeholders worldwide. So more capacity is never a bad thing. So to tell you a little bit about the goals and the work of which we IBCCF. It is a platform for mainly academic scientists. So although we're trying to get our work to government, it's really a place for us to kind of put our knowledge. We're also trying to keep it distinct from industry science because we think we sort of need that for our legitimacy. It's more comprehensive, more systematic, and more timely input to decision-making process is what I'd like to do. More comprehensive in the sense that we want to leverage all scientific fields that are available, that are relevant to our problem, and not just the ones that tend to work on one thing or another. And also for different positions within a field or discipline, not just the prevailing knowledge for people with different ideas. More systematic and timely in the sense that scientists could be informed in more detail about the needs of decision makers and how decision making is actually done. What's the content needed? What are the schedules? What are the deadlines? The organization of that is currently, and I don't think I need to update this number, I think it's still current. Global network of scientists from more than 40 countries in all continents, representing chemistry, toxicology, ecotoxicology, engineering, epidemiology, medicine, and it is now an association according to Swiss law. And if you're interested and haven't heard about it before, please go to the website and come and bug me afterwards if you want more information. And the way that the IBCCF is planning on doing its work is through putting together working groups and project consortia that address priority topics in a flexible way, and to create these IBCCF reports. And the IBCCF reports will summarize the state of the science, talk about agreement and disagreement among scientists and try to come to some sort of consensus, major uncertainties and knowledge gaps, what are the research needs, and what are the potential implications of the current knowledge policy. I think that's all I have, and I'll just mention that Ricardo Barr is involved right now in one of the first IBCCF projects where we have this training workshops. We're doing this with 3 countries, with Chile, Ghana, and Armenia, although Armenia is kind of missing, so we don't want to mention that. But we're really trying to install what are national principal scientists, these are the guys who are responsible for bringing groups together to bring more capacity between scientists. So we're going to have some experiences so far. Take any questions about that?
Have you had any experience with industry oil and interface with the environmental regulation and the industry? Have you had any experience with this?
With industry partners or with?
No, I mean in terms of new regulation for the industry. Petroleum, I think. I'm concentrating petroleum industry.
No, not.
You have to put this kind of frame then afterwards in the national regulation. And IPCP is a science community which would then consult to the Stockholm Convention, and then maybe if the Stockholm Convention take a step for a chemical, then finally you put it in national regulation. Yeah, at the moment you cannot make something on international level for regulation directly for the country. Yeah, so the legislation is always national for implementation.